So to show that a number is a zero of the polynomial, you have to do synthetic division. And what is it we're looking for with synthetic division? Remainder of zero. Exactly. So we need to do synthetic division on the number 2. We're performing synthetic division using the number 2. Inside the upside down synthetic division bar, we have just coefficients. If we get a remainder of 0, that shows that this is a 0 or an x-intercept. So let's keep our fingers crossed. And would you look at that? We got a remainder of 0, which proves that x equals 2 is a 0, but it also means this, and this is kind of more important than what we just did. If x equals 2, write this down. If x equals 2 is a 0, comma, then parenthesis x minus 2, parenthesis, is a factor of p of x. Here's the reason this is so incredibly important. Please listen carefully. If we went back up to the original polynomial and I asked you to factor it, here's what you would try to do, and this is what you should try to do. You would factor by grouping. Right? I don't want you to write this because it actually doesn't work. I want to show you that it doesn't work. But if you tried to factor by grouping, from this first group you could pull out an x squared, and that will leave you with what? X plus 2. But from the second group, what can you factor out? It doesn't have a common factor, right? So this does not factor using known factoring techniques that you're used to, but it still does need to be factored. Eventually, when we finish 3.4 and 3.6, something like this does need to be factored, but it doesn't factor using the traditional way. We've already found a factor, though, using synthetic division. One of the factors is x minus 2. So what we can do is partially factor p of x now. Instead of p of x equaling this original polynomial, we know that p of x now equals x minus 2 as one of its factors. What's the remaining factor? What is... Exactly. Where'd that come from? You guys listening? He's absolutely right. These numbers are the coefficients of a smaller of degrees that's one smaller than the original polynomial. We started with x to the third. We factored out an x minus 2. So that means these are the coefficients of an x squared polynomial. X squared plus 4x plus 5. So what we've done using synthetic division is partially factored p of x. It's not fully factored, because if we start with a third degree polynomial, how many factors are there going to be? If it's a third degree polynomial, there's going to be 3 factors. We've only got 2 of them, so we are going to have to eventually split that up into 2 more factors. But what's the problem with x squared plus 4x plus 5? It does not factor. Using known factoring techniques. We're going to learn how to factor that using an unusual way, but eventually what p of x is going to have to look like is this. X minus 2 times 2 more factors. Those 2 factors we haven't been able to find up until now. But does that make sense, the direction we're heading? Okay, once you find a 0 that you know is a 0 because you get a remainder of 0 using synthetic division, then you start to factor the polynomial. Why would we want to write the polynomial in fully factored form? Because we need to find all 3 zeros. All we've found is one of the zeros. We need to find the other 2. The other problem is, and this is what we started talking about last time, I already gave you as part of the problem that x equals 2 is one of the zeros. Okay? We learned last time about, and let's get back into our lesson now. We learned last time about something called the rational zeros theorem. It gives us a list of possible rational zeros. If I don't give you a number to test in the first place, how do you know what numbers to plug in to see if they're zeros? There's an infinite list of numbers. You could start testing all of them if you want, but if you use the rational zeros theorem, at least it gives you a little bit smaller list to choose from. And this, I think, is where we were. Example 1. We use the rational zeros theorem on this polynomial. And we just barely started testing. We took the first number, positive 1, tested it. Didn't end up working. So let's keep going. Let's test another one. Positive 1 didn't work. Let's try negative 1. Does negative 1 provide us with anything? Go ahead and try it. Try negative 1. Does that work? Does negative 1 work? Well, that doesn't work. Keep trying then. Go to the next number in the list, see if that one works.
I went through all of them and I got everything out of remainder.
Get out of here.
Yeah. Actually did them twice.
No, you didn't.
Yeah. Yeah, I did. Erase the whole thing because I thought I made a mistake.
Alright. What is the next number in line? Positive 2?
Remainder of 2.
No.
Yes, it is.
Yeah, when they started getting to the bigger numbers, I didn't even go out because it was saying I'm getting remainder like over 100. Yeah,
Holy moly. Remainder of 100.
Wow.
something over it.
Let's try 2.
This did not work out as well as we hoped. It's still recording, right?
Correct. Alright, that gives us a remainder of 2.
Everything we've learned is follows.
No, no. Are you sure none of the numbers work?
Yeah,
Absolutely.
I went through all of them. It worked. I know at least 4 of them should have worked.
We should have.
There should be 4 zeros. Or at least 1 with the multiple zeros.
No.
Then, this equation is wrong.
No, there's nothing wrong. Here's the thing, you guys.
Zeros false.
You listening carefully? Everybody look up at the screen. It has to do with the name of the test. What does the word rational mean? Not quite real. Rational numbers are real numbers, but they're a special type of real number. What does the word rational mean? Whole numbers. Whole numbers are rational numbers, or
Fractions that have an end.
fractions.
That have an
Okay.
end.
Here's the thing you guys need to realize. Listen carefully.
Some fractions.
Zeros of polynomials don't have to be real numbers. They could be imaginary. Though they don't also have to be rational numbers. They could be irrational. Okay? The problem with this rational zeros theorem is it only provides a list of possible rational zeros, but that does not guarantee that the zeros of the given polynomial are rational. They could be irrational, or they could be imaginary. So considering that none of these numbers work, that doesn't mean that p of x doesn't have any zeros. It doesn't mean that we did anything wrong. What does it mean about the type of zeros of p of x?
They're not rational.
They're either not rational or imaginary. And that's the one drawback for this test, is this test only gives you a list of possible rational zeros. Unfortunately, if your polynomial has irrational zeros or complex or imaginary zeros, this test doesn't work. Okay, so that's something that you do need to realize with this. Okay, so you guys didn't do anything wrong. None of them actually work. That doesn't mean that this is a bad polynomial. It's just unusual that it doesn't have any rational zeros. Let's try example 2. Yo! We haven't learned how to find them yet if they're not rational zeros.
You have them? Could show us.
That's 4 point, not 4 point.
Well, exactly.
We wouldn't be able to do anything yet, so we're just going to move on. Not for this section, no. It might be on 3.4 or 3.
4.4.
What's the next what section is this?
3.4.
So 3.6. 3.6 maybe. Let's try this one. Let's see if this one has any rational zeros. The last one did not. This one hopefully does. X to the 4th minus 5x cubed minus 5x squared plus 23x plus 10.
Finally, you were nice and gave us all of the x values.
So, use the rational zeros theorem to list possible zeros. So, the rational zeros theorem means we have to find the factors of p, we have to find the factors of q, and we got to divide them. So what are the factors of p?
Plus or minus 1.
What is p, first of all?
10.
P is 10, the constant. So factors of that are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Factors of q are plus or minus 1. Are you even taking notes? Let's get out some paper. P divided by q, if you take all the factors of p and divide them by plus or minus 1, then p divided by q is just plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. So, let's try it. You guys can do this. Start going through the numbers until you find one that works. One does work here. Not the number one, but one of these numbers from the list does end up working.
Only one?
Well, one at least, yeah. Q is the leading coefficient. Sounds like there's some teamwork going on over there. That's good. That's good.
Would you like teamwork opportunities on the test?
Very interesting.
Don't just try the positive ones, try the negative ones. Try.
Sure, one doesn't work. Okay.
Does x equals 1 work? 1 does not work?
Fine.
Alright, try negative 1. Wait a
Doesn't work
minute.
either.
Negative 1 doesn't work? Valerie, you said you might have found one? There's 2 of them that work? So, Valerie's claiming that you say negative 2 works? Let's try negative 2. You might be onto something. Will you look at that? Now, everybody listen carefully, because I'm going to show you something that's going to save you a lot of work. A lot of work. A ton of work. We found a 0, correct? Does that mean this is the only number that may work from the list? No, and it sounds like some of you have found another number, but here's what you need to do. Okay? Before you start testing more numbers with the original polynomial, I do need you to do this. If x equals -2 is a 0, what's the factor that matches that 0? X plus 2. So after every time that you find a potential 0, I want you to partially factor the polynomial. So p of x started out as a 4th degree polynomial. We now know that one of the factors is x plus 2. The remaining factor that's a 3rd degree polynomial is x to the 3rd minus 7x squared plus 9x plus 5. Where did this 3rd degree polynomial even come from? Am I just making up numbers here? It's from the synthetic division. It's from these numbers right here. Now here's why this is so important. Everybody look up here so I know you're paying attention. Are there still zeros remaining to be found of the polynomial? Yes. Any remaining 0 of the original polynomial is also going to be a 0 of this polynomial right here. Are you listening carefully? Did you guys all hear what I just said?
Yes.
Any 0 of the original polynomial at this point is also going to be a 0 of this polynomial right here. And what's the practicality of testing now on the smaller polynomial? It's smaller. The numbers are smaller. And also take a look. Take a look at the p divided by q. If this is q right here and if this is p right here, isn't your list of possible zeros cut down now?
Yeah, it's either positive or negative 5.
You don't have to test plus or minus 10 anymore, because that wouldn't be a factor of this smaller polynomial. So once you start testing numbers again, instead of using the original polynomial, use these numbers. And here's what I mean by that. Valerie said, or somebody over there said that 5 works. Watch carefully. I'm going to test 5 synthetically, but I am not going to use the original coefficients of the polynomial. What coefficients are we going to use?
The new one.
The new one. 1, -7, 9, and 5. Not only are there less numbers to use, here's the other reason why you're going to want to use the smaller polynomial and not the original polynomial. Haven't we found 2 zeros now? Which means we've also found 2 factors. The other factor we just found is x minus 5. After every time you find another 0, refactor the polynomial. We now know that it equals x plus 2 times x minus 5 times an even smaller polynomial now, x squared minus 2x minus 1. Had you gone back and used the original polynomial again, would you have been able to find this smaller polynomial?
Yes.
Eventually.
No. You wouldn't. If you had gone back to the original polynomial, you wouldn't have gotten it down to this 2nd degree polynomial. Now, we're still not done yet. Didn't we start with a 4th degree polynomial?
Yeah.
How many factors do you see there?
2.
Nope. 3. We have 2 linear factors and we have a quadratic factor. We have 3 factors. We're part of the way there, but we are not done yet until we've factored p of x completely. So consider this now, you guys. This polynomial that I just circled. Does that factor using traditional factoring techniques? No. Here's what that means. There's 2 things that means. Are you listening carefully to this? If this does not factor using normal factoring techniques, that also means that this list that we made is now useless. None of those numbers are going to work anymore. Because this is only rational zeros. If something doesn't factor, that means that zeros are what type of zeros? Irrational or imaginary. The only way to find them now, unfortunately, is the quadratic formula. So we have to do the quadratic formula on this little guy here. X equals the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula. Here it comes. X equals the opposite of b, which is positive 2, plus or minus. And I'm going to go really fast through this because this is algebra 2 stuff. B squared is 4 minus 4 times A times C all over 2A, which is 2. Inside the square root, 4 minus 4 times 1 times negative 1 turns into 8. So what's the square root of 8? All over 2. Now you have to simplify square root of 8. That turns into 2 square roots of 2 all over 2. This is stuff that you're going to have to do fairly quickly. Okay? Now,
So plus or minus square root of 2.
not exactly, no. This is not the final answer either. This can simplify a little tiny bit further.
Divide.
If you consider just those two numbers right there, what can you factor out of just those two numbers? So if you factor out a 2, that gives you 1 plus or minus 1 square roots of 2 all over 2. This 2 cancels with that 2. So your answer is 1 plus or minus the square root of 2. Now, how many zeros is this? This is really 2 zeros because it's two numbers. It's 1 plus the square root of 2 and it's 1 minus the square root of 2. Okay? How many zeros have we now found? All 4 of them. 2 of them were rational, 2 of them were irrational. Okay? So I want you to make a list of your zeros over here. The zeros were x equals negative 2, x equals positive 5, and x equals 1 plus or minus the square root of 2. Those are all 4 of your zeros. On your test, I want you to list it this way so I don't have to go searching around the entire planet to find where you eventually found the zeros. Okay? Make it in a box so it's easier for me to find. Second thing I need you to do is write p of x in fully factored form. That means there needs to be 4 factors of p of x. The first 2 are easy. X plus 2 and x minus 5. The other 2 factors are a little bit easier, a little bit harder to find, but not super hard. Here's how it works, you guys. Some of you are really good about doing things, but some of you aren't really good about understanding really what you're doing. Like this here. How do you know that x equals negative 2 is going to give you a factor of x plus 2? Some of you have just memorized the fact that it works, but you don't know why. Why is it called a zero? If I add it, so if I took this, x equals negative 2, and added 2 to both sides, now what does it equal? X plus 2 equals 0. That's why the factor itself is x plus 2, because it equals 0. So if you apply that same concept to this, x equals 1 plus the square root of 2, and x equals 1 minus the square root of 2. If we could get these equal to 0, that would tell us what goes inside the factor. So let's watch carefully. If I subtract 1 on both sides and subtract the square root of 2 on both sides, then doesn't that side now equal 0? What does the other side equal? X minus 1 minus the square root of 2, and that equals 0. Now that it equals 0, that's what goes inside the factor. X minus 1 minus the square root of 2. What is the other factor going to be? X minus 1 plus the square root of 2. Those are all 4 factors of the original polynomial p of x. The only difference, are you guys listening carefully? The only difference between this is 3.4 and 3.6. 3.6 is called imaginary zeros of complex numbers. These are called real zeros of complex numbers. So what do you think the only difference is going to be in 3.6? Some of these are going to have I in it, that's all. The process is exactly the same. You start with the rational zeros theorem, you test a couple of them. Once you get it down to a quadratic factor, you have to use the quadratic formula, and you're either going to get irrational zeros like this one, or you're going to get complex zeros, like in 3.6.
And we could be doing math with eyes in it just in time for Halloween.
Yeah. Good thought. Let's try example 3. Find all zeros. And factor. So, the polynomial is x to the fourth minus 5x squared plus 4 These sorts of problems always start the same way. If you don't know what numbers to test, you have to make a list of possible numbers to test. Where does that list come from? What is it called? The rational zeros theorem. Use rational zeros. Use the rational zeros theorem. You first list your factors of p, then you list your factors of q. By the way, in case you're wondering, all the polynomials we've done up until this point have always had a leading coefficient of 1. Do you think it's always going to be that way? No, it will not. These ones have, because it is easier that way, but we're going to do a few more challenging ones here in a second, where the leading coefficient is not 1. But the factors of p are plus or minus 1, plus or minus 2, plus or minus 4. Factors of q are plus or minus 1. So when you divide all the factors of p by all the factors of q, then p divided by q is the actual list, which is plus or minus 1, plus or minus 2, and plus or minus 4. So that's your list of possibilities. It is not guaranteed that any of those will work. This might be, again, a polynomial that only has irrational roots, or it might have all complex ones, but didn't I just say that? Raise your hand if you heard me say that like 5 minutes ago. So you were the only one that did not hear that. Hang your head in shame. What is the answer to that question, you guys?
No.
No. Yes. We'll get to that in our next example. So start doing synthetic division until you find one. Ooh, good point. There are missing terms. Aren't there missing terms?
And found the 0, and you guys are still looking for missing terms. 1 is a 0. I mean, find that for yourself.
How many are we supposed to find eventually? 4. We're supposed to find 4 because it's a 4th degree polynomial. Not all 4 of them are going to be in that list. That's only a list of rational zeros. Has anybody found one? You found 2? What are they?
No, not negative 1. I got 1.
Uh-oh.
Negative 2 and 1. Positive 1.
Positive 1 works?
But negative 1 does not work.
Well, let's try positive 1. Let's see if that one works. So you guys did put the zeros in there, right? The missing terms, you had to put a 0 in its place. So if you drop down a 1, 1 times 1 is 1, 0 plus 1 is 1 times 1 again, that's negative 4. Add that to get negative 3. Add... Wait, no. That's a negative 4. I was going to say, I messed up somewhere. That's negative 4. 1 times negative 4 is negative 4. We do get a remainder of 0. Hey, that's awesome. Again, instead of going right back to the original polynomial, factor it, or at least partially factor. You now know that one of the factors is x minus 1. The smaller factor is x to the third plus x squared minus 4x minus 4. So now continue on. Did somebody say the negative 2 might work?
Zeros are negative 2, so you're negative 1.
All 4 of them are rational? That's incredible.
No, not negative.
So, did I hear a positive 2 works?
None of the plus or minus 4s are.
So if you now test positive 2 on the smaller polynomial, we have 1, 1, negative 4, negative 4.
Not 4.
So we found another 0. X equals 2 and x equals 1 both work. Hey, take a look over here for a second, you guys. I'll let you finish this up in just a second, but I just want to make you aware of something. The work that I'm showing here, I've already found 2 zeros, so I've partially factored p of x into x minus 1 times x minus 2 times this quadratic. Instead of continuing to do synthetic division, consider the quadratic that you now have. Doesn't this factor?
Yeah.
So you don't want to go through and test more zeros. You can just find them by simple factoring. It factors into what?
2 and 1.
X plus 2 and x plus 1.
That's kind of weird because when you did x minus 1, it didn't work.
Well, that was originally.
Negative 1 didn't work?
If you did not the first equation, it didn't work at all.
Get out of here.
It doesn't make any sense.
Let me show you something else that is very hard to see sometimes, but if you can train yourself to look at this, then it'll save a lot of time. Consider the original polynomial. Or actually, consider this polynomial that I'm going to write in red. If I had asked you to do this one, x squared minus 5x plus 4, doesn't that factor? Doesn't, it factors, right? This factors into negative 1 and negative 4. You guys are going to want to pay attention to this. Is there any similarity between the one in red and the one in black? The one in red and the one in black.
There's a crucial problem.
It's like the same.
Not quite the same.
This is something you guys got to do next year in calculus. If you can get good at it now, you're going to be a lot better next year in calculus. This is what's called substitution.
Oh, I thought you were going to say you suck.
Some of you do, but no, this is called substitution. Those that bleed blue is what I'm talking about.
Hey, you know what?
Shh, shh, shh. Your eyes are going to really want to watch this. Let x squared equal u. Let x squared equal u. Now you also have to be familiar with some of your properties of exponents. Do you guys agree with this, that x to the fourth is really just x squared squared? And what is it that we're going to let x squared equal? So instead of writing x to the fourth, what is the first term going to be? U squared. What is the middle term going to be? Minus 5u plus 4. So this polynomial turns into p of x equals u squared minus 5u plus 4. Now doesn't that factor?
Yeah.
What does it factor into?
Negative 4 and 1.
This factors into u minus 4 times u minus 1. But what is u equal to, really? Isn't u really equal to x squared? So now go back and unsubstitute. This really turns into x squared minus 4, and this is x squared minus 1, which are both difference of squares. So this factors into x minus 2, x plus 2. And that factors into x minus 1, x plus 1.
Oh, that's so much easier.
You guys will be doing a lot of u substitution in calculus. It's a really good skill, first of all, to recognize, and second of all, to use u substitution. You can only, that's a good question. You can only use u substitution if your middle exponent is half what the largest exponent is. It has to have that property. If your middle exponent is half of this exponent here, and if there's 3 terms, because it would resemble a quadratic. So anyway, let's do a significantly harder problem here.
Oh, really?
Oh yeah.
Well, we just take a nap.
No.
Nap time would be off.
Example 4.
Bye.
Wait, let's all make sure that Addie's got it. Addie, are we always going to have a leading coefficient of 1? All right. This one does not. 6x to the third plus 11x squared minus 3x minus 2. What are the factors of p? Plus minus 1, plus minus 2. What are the factors of q now, though? Plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Watch carefully to how this works. P divided by q. You have to take each factor of p separately one at a time and divide it by everything that's in q. So if we just start with the 1 and divide it one at a time by all the factors of q, plus or minus 1 divided by plus or minus 1 is plus or minus 1. What's plus or minus 1 divided by plus or minus 2? Plus or minus 1 half. Plus or minus 1 divided by plus or minus 3 is plus or minus 1/3. And plus or minus 1 divided by plus or minus 6 is plus or minus 1/6. Now move on to the next factor of p and do the same thing. Plus or minus 2 divided by plus or minus 1 is plus or minus 2. Now watch carefully. You can save yourself a little bit of room. What's plus or minus 2 divided by plus or minus 2? Plus or minus 1. And we already have that one. You don't need to write it again. You already have a plus or minus 1 right there. Okay? Plus or minus 2 divided by plus or minus 3 is plus or minus 2/3.
Another plus or minus 1/3.
And plus or minus 2 divided by plus or minus 6 is plus or minus 1/3, which we already have. Now, we have a list of possible rational zeros. Some of them are whole numbers, some of them are fractions. Rational numbers means whole numbers and fractions, so this is still okay.
As long as fractions, or as long as fractions end, you know, the decimal
No, as long as the decimal either ends or has a repeating pattern.
ends.
So let's test the whole numbers first. We might get lucky and find the whole numbers rather than having to use fractions. So let's test plus 1, and then we'll test minus 1, we'll test minus 2, we'll test plus 2. And keep your fingers crossed. Oh, everybody stop. Sorry. There's one other thing I want you to... I just like to show you some shortcuts every now and again to help speed up the process. This is a 3rd-degree polynomial, yes? So, hypothetically, one of these in that list could be a 0, correct? If we do find one 0 and we partially factor the polynomial, then we're going to have something in parentheses like x minus 2 or x plus 2. But what's the other part in the parentheses going to be? It's going to be quadratic. So do we have to do any more synthetic division at that point? Once you've factored it down to the last term being a quadratic, you're done with synthetic division. Why? You can find zeros from a quadratic either by simple factoring, or if it doesn't factor, you can find them by the quadratic formula. So we're only going to have to find one zero using synthetic division. The other is going to be found by either the quadratic formula or by simple factoring. Does that make sense what I'm talking about?
Yeah.
Does +1 work? No good? -1 doesn't work?
-2 works.
Hey. Let's try that -2 then. 6, 11. What? You tried 1/2?
Yeah.
Cool. Okay, check it out. Shh, shh, shh. Jacob was right. X equals -2 does work. That means the factor is x plus 2. That also means the remaining quadratic factor is 6x squared minus x minus 1. Now, if given the choice, consider this. If given the choice between using the quadratic formula or factoring, which one would you choose? Factoring. Now, I'm not saying this one factors. Maybe it does, maybe it doesn't. But rather than jumping right into the quadratic formula every time, you might want to try to factor it. What's 6 times -1? -6. Is there any factors of -6 that can add to -1? -3 and 2. So this factors into 6x squared minus 3x plus 2x minus 1. If you factor now by grouping, you can factor out a 3x, and that leaves you with, let's see, that leaves you with a 2x minus 1. From this second group, there's nothing to factor out save a plus 1, so you factor out a plus 1, that leaves you with 2x minus 1. That means it factors into 2x minus 1 times 3x plus 1. Which means your two zeros are x equals 1/2. We've been done told. And x equals 1/3. So the zeros, remember, please remember to do this so I don't have to search all over your paper. List the zeros. I just lost one of them. Where was it? Oh, right here. X equals -2. X equals 1/2. And x equals -1/3. Now also factor your polynomial into x plus 2, 2x minus 1, and 3x plus 1. Addie, are you feeling exceptionally brave today?
To do what?
Would you like to come up to the board and show us how you tested 1/2? Thank you. Because you did it, right? And it worked?
Yeah.
So grab that little pen over there. Okay. She is now the teacher.
Okay, so what I did is I basically did the same thing for the synthetic division.
That's pretty cool, isn't it, by the way?
Yeah, I like that. I just put 1/2 here.
Somebody tell her the numbers. 6.
-3
And what?
-6.
Okay, so I got 6 down and I divided it by 2. So I just did 1/2. And it was 3, and then 14, and divided by 2 was 7, and that was 4, and that was 2, and 0.
So was it really as bad as you thought it would be to do fractions? Thank you, Ed. That's very brave of you to try to do.
That was cool. I like writing on that board.
That's kind of fun. Okay, now that's the end of 3.4. I think we can sum up 3.6 in only one problem, because the only difference between 3.4 and 3.6 is some of your factors are going to have I in it instead of, so let's finish this up.